Okay guys, so in this video we're going to talk about applications to physics and engineering. And to be honest, I don't really care that much about many of those applications because that's just not really something that I find all that interesting comparatively to some of the other aspects and applications that we talk about. So really this could probably be just talked about in terms of the one application in physics and engineering that Andy finds very interesting. And that is going to be the moments of centers of mass. And to be honest, this is actually going to be helpful as well when we get into concepts of probability, which I do find interesting. So, essentially, the idea in this section is to find some point P here on which a thin plate of any given shape balances horizontally. This is going to be the center. And to be honest, it's the center of mass, and we can actually deal with finding this when the density varies. So, you have something with a varying density depending on where you are. Maybe one side's more dense than the other. We can also do that, but we're going to stick to pretty simple stuff where it's a uniform density. But this point here is called the center of mass, or the center of gravity of the plate. So that's what we're going to be talking about. Now, this is actually based on the law of the lever, which was an Archimedes discovery functionally, that if two masses, mass 1 and mass 2, are attached to a rod of negligible mass on opposite sides of a fulcrum at distances d1 and d2, so that is, the mass 1 has a distance 1 from the fulcrum and mass 2 has a distance 2 of the fulcrum, then the rod will balance if the mass times the distance is equal on either side. So this is essentially where this is derived from, is just on Archimedes' law of lever. And again, if you want to see kind of this derivation from the law of the lever to what we're talking about, the book and many other places definitely have those, but I'm not going to waste too much time with that. Instead, I'm just going to talk about essentially what we get to. So through derivations of this law of the lever, we end up with the center of gravity occurring between two functions, f of x on the interval from a to b, with area a at the point x bar, y bar, which we often describe as like mean. So this is kind of like the mean x and the mean y. That's what we're actually finding, is the average x, average y, where we define x bar as 1 over a, integral a to b, x, f of x minus g of x dx. So that is 1 over the area of whatever we're talking about, times the integral of x times our f of x and g of x. This is one function, here's the other one. And y is described as 1 over a, area, integral from a to b, of 1/2 f of x squared minus g of x squared dx. Now, these formulas assume the density of the object is uniform. There are more complex aspects to this. There are more complicated formulas dealing with maybe a density function as well, if you want, but we're going to just stick to uniform density. I'll leave that to a physics class or whatever for you. Okay, so in simpler terms, if we are dealing with a region bound by the x-axis rather than some other curve, we can actually just use this, because if the other curve is just the x-axis, then we're good here. So these are a little bit simpler, and in general we're going to be using this when we're talking about some region, but that region could be bound by two curves. So in that case we'll go to the more complicated one, but when we can get away with it, we'll stick to the simple formulas. Alright, so let's take a look at an example of these things. So find the centroid of the region bound by 2x plus y equals 4, x equals 0, y equals 0. So let's start with the graph of this thing. So we have something like 2x plus y equals 4. So we end up with x and y as well being a boundary line here for this. And if you notice, this is a triangle. Okay, so we expect, I would assume that maybe the average point is probably going to be somewhere around here-ish. And so when we get it, it's good to graph that point when you find it and just make sure that it is believable. Okay, so we'll do that in just a bit. Now, again, since we're bound by some other, we're not bound within some other functions, we'll just use these simple ones here. And I'll go ahead and just paste it in here so we have it. since if we have a nice formula to work with, we might as well just keep it handy. Okay, so basically, we have our x bar is equal to 1 over a, our area. So first of all, we need to find our area. Now, if you remember, the area is the integral from, in our case, either 0 to 2 on the x-axis or 0 to 4 on the y-axis. It doesn't really matter. I think I'm going to go with the x-axis, and then the height here is kind of our y. So, and the reason I'm going to do that is it's easier to solve for it here. So if we think about this y equals negative 2x plus 4. I think I'll leave it as that format. So let's start with the area. The area is the integral from 0 to 2. And so we're going along the x-axis, so that's going to be a dx. So I'm just going to find this thing in terms of x's. So negative 2x plus 4. Okay, so we end up with our area is equal to the integral of negative 2x is going to be negative 2x squared over 2 plus 4x from 2 to 0. So that means our area is going to be 2 squared is 4 times negative 2 is going to be negative 8 over 2 is negative 4 plus 8 minus, now we plug in 0 into these, that just gives us 0. So our area here is 4. Now, this is probably pretty overkill, because if you think about it, what shape is this? This is a triangle, so it's 1/2 base times height. Base is 2, height is 4. 1/2 of 2 times 4 is 4. So, I mean, yeah, we could have used calculus, which we did here, but sometimes there are much more easy ways to find those areas. So just something to be aware of. We could have just used, since it's a triangle, could have used the area of a triangle formula. That would have been way easier. All right, so regardless, we have A, our area. So we're going to now plug it into our formula here. X bar is equal to 1 over 4 times the integral from 0 to 4. We're going to do it along the x-axis again, and it's not 0 to 4, I'm sorry, it's 0 to 2. This was 0 to 4. 0 to 2. And we are going to take x times f of x, which again, in this case, our f of x was just our negative 2x plus 4. Negative 2x plus 4 dx. All right, so if we're going to integrate this, I'm going to distribute. We get x bar is equal to 1/4 times the integral from 0 to 2 of negative 2x squared plus 4x dx. And so integrating this thing, we get x bar is equal to 1/4 times the integral, well, I'm going to write that in just a sec. X bar is equal to 1/4 times, this would be negative 2x cubed over 3 plus 4x squared over 2. And we're going to take this thing from 2 to 0 and find our x bar. Okay, so 2 into this thing is going to be 8 times negative 2 is 16. So we have 1/4 times negative 16 over 3 plus 4 times 4 is 16 over 2, which is going to be 8 times our 1/4, because it is getting distributed. I need to be careful with that. Minus, and then we have our 1/4 times this whole quantity with 0, but it's just going to be 0 here, so that's gone. And we end up with these 4's simplifying down to negative 4/3 plus 8 over 4 is 2. So that would be negative 4/3 plus 6 over 3, which is 2/3. So that's going to be our mean x value. Now let's think about that real quick and make sure that that makes sense. X equals 2/3. Okay? All right, so this is the center of it in terms of x. Now we'll find the center of it in terms of y, but first of all, that's believable. It's somewhere inside of it. That's the first thing that we need to check. The next thing is that once we find the other value, we'll just double check that that's something we expected. Okay, so now we're going to use our y bar. So I'm going to go to y bar. Y bar is equal to 1 over a times the integral from a to b of our f of x squared. So 1/2 f of x squared. Okay. Okay. So dx, obviously. So again, same thing as before. We have y bar is equal to 1 over 4, our area, from 0 to 2, 1/2 times f of x. Our f of x is negative 2x plus 4, and we're going to square that. Negative 2x plus 4 squared dx. And again, if we were doing this in terms of y, this would be a dy. Our bounds of integration would be along the y-axis, and we'd need to write this in terms of y instead of terms of x. Just something to be aware of. So y bar then is going to be equal to 1/8 times the integral from 0 to 2 of, I'm going to distribute this out, that would be 4x squared minus 8x. Minus 8x is going to be minus 16x plus 16. And now we can integrate this. We end up with 1/8 times 4x squared, so that would be 4x cubed over 3. I'm just putting this 1/8 in. Minus 1/8 and 16 just makes 2 times x squared over 2 plus 2x. And we're going to take this thing from 2 to 0. So our 4, that makes that 2. These cancel here. We're left with x cubed over 6 minus x squared plus 2x. And we're taking this from 2 to 0. So plugging into here, we get 8 over 6 minus 4 plus 4 minus 0. So these 4's drop off, and we get 8 over 6, which they're both divisible by 2, so that would be 4/3. So this is our y bar. So the center of mass, the balancing point, is going to be at x equals 2/3 and y is 4/3. So 2/3, 4/3. This is the point that should be our center. So let's double check that. 2/3, 4/3. Now, this is about where I was saying I expected it to be, so that's pretty good. So this right here is our center, and again, it's believable. That's important to note. Okay, let's take a look at another one. Find the centroid of the region bound by y equals 1/2 x squared, x equals 5, y equals 0. Okay, so first of all, let's start by graphing this thing. We have 1/2 x squared, we have x equals 5, and y equals 0. So we are bound in this kind of region here. Okay, so in general, this is basically a triangle, just like our last one was actually a triangle, and so we can at least get some estimations based on the shape. I would say probably similar concept to our other one, maybe somewhere around about here-ish is what I'm expecting. So we could actually, I mean, if you want to just guess, right, this would be like, I don't know, 3.5 and somewhere around about, I don't know, 3.5 as well. Somewhere here-ish. This is our guess. And so I just want to put this up against where it's going to actually be so that we can get an idea of kind of whether our answer makes sense. So it is important to just kind of think about it logically. It's like, where do I expect it to be? So if I get anything that's way off, I know I made a mistake. Okay, so again, same thing. We have some boundary. And so we want to use kind of a simple choice here. So we're going to use this one. And again, I'll just pull this in so that we have it for reference. Okay, so first of all, we need our area. And so our area here, area is the integral from, we can do however we want. We could either do it here for y from 0 to 12.5, but I think along x still makes the most sense from 0 to 5. So this is from 0 to 5 of 1/2 x squared, especially since we have solved for y equals here. It's easier that way. Okay, so 1/2 x squared, if we integrate this thing, this will be 1/2 x cubed over 3 from 5 to 0. So that means that we are going to have 5 cubed is 125 over 6, and this is our area. Now, we'll double check 125 over 6, that it doesn't simplify. It doesn't. Okay, so that's our area. Now, if you think about it, 1 over area, so that is 1 over a, that's just 6 over 125, so I'll probably just write it like that. Okay, so let's find our x bar first. X bar is equal to 6 over 125, our 1 over a, times the integral from 0 to 5 of x times 1/2 x squared dx. So that means that x bar is equal to 6 over 125 integral from 0 to 5 of 1/2 x cubed dx. Now we're going to go ahead and integrate this. I could also pull this 1/2 out. This becomes 1, this becomes 3. So we end up with x bar is equal to 3 over 125 times the integral of x cubed. That's going to be x to the 4th over 4 from 5 to 0. Okay, so plugging in our 5 now, we're going to get some ugly numbers. All right, so 5 to the, or excuse me, yeah, 5 to the 4th over 4 times 3 over 125 is going to be 15 over 4. That's not too bad. Minus 0. So that means we found our x bar. X bar is 15 over 4. 0 into this, 0. Okay, so we have our x bar. Now we're going to go to our y bar. So as a reminder, y bar is equal to our 1 over a, 6 over 125, integral from 0 to 5 of 1/2 f of x squared, which is 1/2 x squared squared. Okay, so first of all, this 1/2, again, will simplify a bit. This becomes a 1, this becomes a 3. We end up with y bar is equal to 3 over 125 times the integral from 0 to 5 of x to the 4th over 4. That's what this is. X squared. Squared is x to the 4th. 1/2 squared is 1/4. There we go. Dx. Forgot to write the dx over here. Okay, so now if we integrate this thing, we get y bar is equal to 3 over 125 times x to the 5th over 4 times 5. So the 4 was already there, and we just had that 5. We're taking this from 5 to 0. Okay, so first of all, 0 will just be 0, so that's nice. We end up with y bar is equal to 5 to the 5th over 20 times 3 over 125 gives us 15 over 4. Okay, now 3.75. 3.75. Man, I was pretty darn close with a guess. So let's take a look at it. So our guess was 3.5. We ended up with our 15 over 4 for both of these. Comma 15 over 4. So this is our actual center, and this is what our guess. So again, it's definitely in the ballpark of where I expected it to be. So that's always good to note again. All right. Let's now think about another problem. Find the centroid of the region bound by y equals sine 2x and y equals sine x from 0 to pi thirds. All right, let's take a look at this thing. we have sine 2x, and we have sine x. Whew. And we are bound between 0 and pi thirds. So we could do this a couple ways. If we call this like, I don't know, y equals, and then we do a squiggly bracket from 0 less than or equal to x less than or equal to pi over 3. Then we're here, and now we can kind of see this region. So we have this region up here and this region down here that we're talking about, and we want to find the center of it. Now, first of all, this side's a little bit heavier than this side, so I'm expecting it to be somewhere in the realm of like here-ish, maybe. So let's call that like 0.58. And where was I? Somewhere around here-ish. 0.5, 0.6, 0.7, 0.8. So 0.75, we'll just say 0.75. So this is kind of where I'm going to guess at. Somewhere in this range is where I'm expecting it. Maybe a little bit down here, but whatever. This is my guess. And I just want to make sure again that it's somewhere that I believe. That's my easiest way to check, is it something believable? Okay, so it's important to note which is our upper function and what's our lower function here. Now, it doesn't, if we take a look at our formulas, now these are the ones we're going to use in this case. Now, if we take a look at this, I like to kind of follow the same basic logic of areas and stuff where we take the upper and subtract the lower one. So when I'm using this, I'm going to keep in mind which one I'm calling my upper and which one's my lower. So I'm just going to call this one like, so here, this black one is, the upper one is sine 2x. So essentially, I'm going to call this my f of x, and then this would be my g of x. Okay. So we're going to go ahead and do this thing. So the first thing we need to do is find the area. So as a reminder, the area is the upper minus the lower. So it's the integral from 0 to pi thirds of our sine 2x minus sine of x. So this is our area, and that's the first thing we need to find. So the integral of sine 2x, that's just going to be, so integral of sine is negative cosine, so we have negative cosine 2x divided by 2, because this is like a u sub here, but it's a simple enough u sub we can get away with it. But if you need it, u is 2x. Okay, now let's take a look at this one. Integral of negative sine. The integral of sine is negative cosine, and negative makes a positive cosine x. And we're taking this from pi thirds to 0. Now, if you don't remember, we can always have our trig cheat sheet. I mean, you know. And we have, this is a pi third, so this is one of our specialty cases, 60 degrees, okay? So we have our cosine and sine. Now, cosine of pi thirds is 1/2. I'll go ahead and do that. I was going to zoom in. There we go. So this is cosine. It's 1/2. But again, if you don't ever remember it off the top of your head, it's not a big deal for my class, but you should at least recognize it as a specialty angle. Okay. So we have cosine of pi thirds, cool, but here we have cosine of 2 pi thirds. So that's also something we have to take a look at. So if we look over at 2 pi thirds, here it's negative 1/2. Okay, so let's go ahead and plug these in. We have negative of negative 1/2 over 2 plus 1/2 minus, now cosine of 0, 2 times 0 is 0, so cosine of 0 is 1. It's a negative 1 though, over 2. Cosine of 0 is again 1. Okay, so simplifying this a little bit, negative and negative makes a positive. 1/2 divided by 2 is 1/4, plus 1/2, plus 1/2, minus 1. So plus, minus. These would cancel with this, because this is 1, this is 1. So we end up with area as 1/4. Okay, so that means that 1 over area is 4. This is what I'm going to use when I'm plugging it into here. All right, so let's start with our x bar. X bar is equal to 4, our 1 over a. That's 1 over 1/4, which is 4, times the integral from 0 to pi thirds of x times our sine 2x minus sine x dx. Okay. Now, in something like this, we have essentially what it looks like is it's going to be some kind of integration by parts for each of these, which kind of sucks, but such is life. All right, so we have x bar is equal to 4 times the integral from 0 to pi thirds of x sine 2x minus x sine x dx. This is what we're integrating. And so as mentioned, these each, I'm going to go ahead and copy them or bring this down so I have more room. Each of these things, it looks like we're going to need to do a u sub for each one. So that is to say, this is like saying 4 times the integral of x sine 2x minus 4 times the integral of x sine x. So let's call u is x. So let's work on this first one here. So that means that dv is going to be sine 2x dx. So du is going to be dx, and v is going to be negative cosine 2x over 2. Okay, we'll do the same logic over here. X is u, sine x is dv. So that means that v, and it's dx. V would be the integral of sine, which is going to be negative cosine x. dx is going to be du. All right, so we have 4 times uv, which is x and negative cosine 2x over 2, minus the integral of v, negative cosine 2x over 2. And this 4 is being kind of multiplied into everything, so I'll just put that 4 here as well. V du, so dx here. Okay. And this is going to be minus. Now we do it for the other one here. uv, u and v, is going to be, so minus 4 times x times negative cosine x minus negative 4 times the integral of v du. Negative cosine x, there's a lot of room for error on the x, v du. Okay, so we need to be real careful with it. Okay. So 4 and 2, that makes 2 here. We have negative 2x cosine 2x. This becomes 1. This becomes a positive. This becomes 2 then. So it's a positive 2. So plus 2 times the integral of cosine 2x, that's going to be sine 2x over 2. Okay. Now we have a negative and a negative makes a positive 4x cosine x. A negative and a negative makes a positive, but then we have a negative here, so it will be a negative minus 4. The integral of cosine is going to be sine x. Now we are taking this thing from 0 to pi thirds. Alrighty. So it's important to, in this case, just to make our lives better, we will go to our unit circle. All right, we're looking at 2 pi thirds or pi thirds basically. So first of all, cosine of 2 pi thirds is negative 1/2. So we have negative 2 times pi thirds times negative 1/2 plus these cancel, and we have sine of 2 pi thirds, and so that is sine of 2 pi thirds is square root 3 over 2 plus 4 times pi thirds cosine of pi thirds is going to just be 1/2 minus 4 times sine of pi thirds, which is going to be square root 3 over 2. Okay, and that's all minus. Now we need to do it for 0. Okay, that would be a 0. Sine of 0 is 0. Cosine of 0 doesn't matter because that's times 0, so that's also gone. And then sine of 0 is 0, so it's all zeros. That makes that nice at least. All right, so let's clean this up just a bit. We end up with a negative and a negative makes a positive. These 2's would cancel. So we get pi thirds plus square root 3 over 2. This 2 would cancel to be 1. This would be a 2, so we'd have 2 pi over 3, so plus 2 pi over 3, minus 4 square root 3 over 2, so minus 4 square root 3 over 2. Okay, now let's just clean this up just a little bit more. We have common or like terms here. This would be a 1 pi third plus 2 pi thirds is going to be a 3 pi thirds, which is just pi, but we'll deal with that. Minus, this is like a 1, that's a negative 4, so minus 3 square roots 3 over 2. So that is to say our x bar, after a lot of annoying integration, x bar here is, well, it's not that bad, but we had to do it multiple times, pi minus 3 square roots 3 over 2. This is our x bar. Now, let's take a look at how good we were on that guess here for our x at least. Oops. X equals pi minus 3 square root 3 over 2. I mean, that's pretty close to what we were thinking. And again, I was actually kind of thinking maybe closer to here, if you remember. All right. So we found our x bar. Now let's find our y bar. Okay, so we have to square these things as a reminder. So I'm going to write the formula first. Y bar is equal to 1 over a, which for us, I should just write the formula. 1 over a integral a to b 1/2 f of x squared plus, minus g of x squared. Something like that, dx. This is what we're dealing with. So something to keep in mind while working on it. We have our nice little formula here. And our y and x, or excuse me, our f of x and g of x, sine 2x, sine x. So f of x is sine 2x, and g of x is sine x. Okay, so cool. We need to square this thing. So we're going to have y bar is equal to 1 over a. As a reminder, our 1 over a is 4. So bring this back down. We have 4 times the integral from 0 to pi thirds. Just a real quick reminder, if we want to square it, we're going to have sine squared 2x, and this squared will be sine squared x. Okay. So we have our 1/2 times sine squared 2x minus sine squared x. All right. So we have this thing here. Okay, and this is all dx. Let's go ahead and simplify this a little bit. This becomes 1, this becomes 2. We have y bar is equal to 2 times the integral 0 to pi thirds of sine squared 2x minus sine squared x dx. Alrighty, so when we're integrating this thing, we're again going to kind of think about them as two different things because these aren't the same. It's a sine squared, but this one's of 2x and this one's of x. But both of them are going to be integrated the same way, basically. When we have, if you remember, if we have an even power of sines or cosines, then we go over to the half angle. So let me pull that up. I could have zoomed out before I did that, but I probably should to find that a little bit. Okay, half angles up here. So we're going to use sine squared here. Okay. So that is to say that sine squared 2x is going to be 1 over 2 times 1 minus cosine of 2 times 2x, which is 4x. So let's go ahead and write that out. Okay. So just to make my life, make sure I'm being really careful, we have 2 times the integral of 1/2 times 1 minus cosine of 2 times 2x, which would be 4x. Okay, minus 2 times the integral, sine again, but this one's just nice sine squared, that's 1/2 times 1 minus cosine 2x. Okay, so this is what we are integrating now along 0 to pi half, or pi thirds. These cancel, and we get the integral from 0 to pi thirds of 1 minus cosine 4x. Now this one cancels as well, and we get minus the integral of 1 minus cosine 2x dx. So because these both have the same bounds of integration, I'm actually going to put them back together. I really shouldn't have split them up to begin with, but I do that just to be really careful with everything. But if you notice, this is the integral from 0 to pi thirds of 1 minus cosine 4x minus 1 plus cosine 2x dx. And so this means that these are gone. And we have the integral from 0 to pi thirds of negative cosine 4x plus cosine 2x. I thought about reordering it into positive first, but thought against it. Doesn't really matter. I didn't want to confuse anybody by switching the angle, the order. Okay. So now, if we're integrating this, this is a nice simple integral. The integral of cosine 4x, that would be the derivative of sine is cosine, so the integral of cosine is going to be sine, and in this case it's a negative sine 4x, and then we divide by 4. Again, u sub u is 4x here. Here, u sub u is 2x, but it's simple enough that you can probably do it without u sub. All right, integral of cosine is again sine 2x over 2. Okay, and we're taking this from pi thirds to 0. Okay, so now we're going to go back to our unit circle. Okay, probably zoom out again. All right, so now we have sine of 4 pi thirds. So sine of 4 pi thirds is going to be negative square root 3 over 2. So we have negative square root 3 over 2 over 4 plus sine of 2 pi over 3. Sine of 2 pi over 3 is again square root 3 over 2 over 2 minus, now sine of 0 is 0. Sine of 0 is 0. Okay, so we'll clean this up just a little bit. Negative and a negative makes a positive. Square root 3 over 2 over 4 means square root 3 over 2 times 1/4 plus square root 3 over 2 times 1/2. So that means that we end up with square root 3 over 8 plus square root 3 over 4. This is our y bar. So we have our first one, x was that, so that was our first value. Now our y is square root 3 over 8 plus square root 3 over 4. All right, oops. That's better. Okay. So again, I was thinking closer to here, but again, our guess is, it's pretty close. So it's believable is the point. So here is our actual center here. Okay. Alrighty, so that is our center of mass. Let's take a look at one more. Find the centroid of the region bound by x plus y equals 2 and x equals y squared. Okay. Let's take a look at this one. X plus y equals 2 and x equals y squared. Alright, so we're trying to find this bounded region. And if you notice, this thing here and this thing, this is really like left hand, right hand here. So in this case, I'm probably going to want to do this in terms of y. So if we're going from like a -2 to 1 here, and also it's going to be easier to solve for this thing anyway, because in terms of x, we'd need a square root to define it, positive and negative. So it looks like we're probably going to do something in terms of y. All right. So first of all, I'm expecting the center point to be, I don't know, somewhere around about here-ish. So we can do a guess again. I like to just have something there and make sure that what I expected is believable. So let's just put it somewhere on this line here. So that would be 1.5. So that would be, I don't know, 1.75. And then that would be down just a tad. So that's, let's say -0.5. Who cares? Somewhere like there-ish, right? So this is our guess. Okay. So first of all, we need to talk about the area. So again, this area here is easier in terms of left to right than upper and lower. So the black one here, x plus y equals 2, is going to be our right-hand side. And this is our left-hand side. So this is like our f of x thing here. But really, we don't really want it in terms of f of x. We want it in terms of y. So we want to have some function in terms of y. So we need to solve for this thing. And we're going to do the same thing here. This would be then our g of y. Okay. So that is to say, we need to solve for x here. So that means x equals -y plus 2. Okay, let's make sure that that checks out. Like x equals -y plus 2. I mean, that's clearly the same thing, right? So it doesn't really matter how we change it. We want it in terms of a function of x in terms of y here. Or I guess x in terms of y, a function of y. All right. So first things first, we need to find the area. And so area is the integral. And so since we're doing it in terms of our y here, dy, it's our lowest point is -2 to our upper point 1. So this is -2 to 1, and we're doing dy. So that's why we need these functions in terms of y. So we have our kind of our right-hand one, our f of y here. That's this thing here. That's -y plus 2 minus y squared. All right. So area is the integral from -2 to 1 of -y plus 2 minus y squared dy. So if we integrate this thing, we have the area is -y squared over 2 plus 2y minus y cubed over 3 from 1 to -2. Okay, plugging this all in, we get the area is 1 squared, that's a -1/2, plus 2 minus 1/3 minus, a -2 squared is positive, so that would be a -4 over 2 minus 4, and a minus, and this would be a minus, that would be plus 8/3. Okay. So I'm just going to type this in, save myself the hassle. -1/2 plus 2. I should really make it so I can see what I'm typing so that I don't mistype something. Minus 1/3 plus 2 plus 4 minus 8/3. And we get 4.5 or 9.5. So our area or not 9.5, 9 over 2, 4.5, 4.5, 9 over 2. So that means 1 over a is going to be 2 over 9. So we're going to use that in our formula. Now, if we go back to these things, these are in terms of x's. The only difference between this and this in terms of y is to change the functions into y's and call them dy's. So this thing, I did copy, we can just continue using, but we'll just call it in terms of y instead of x. Okay. So we have that. I'm going to snip these functions again just so I have them down here. This thing. Terribly large there. Let's bring that down. Okay. So in this case, now if you think about this thing here, let's go back to the graph. So we have our 9/2, that's our area, whatever. Basically, if we were to take this thing out, let me snip this real fast. Now, I wonder if I can rotate this. It doesn't seem like I can. Dang. Okay, well, let's just pretend we rotate it. So turn your head, right? So essentially, if we're thinking about it from left to right here, this is our left, this is our right, this is our upper, this is our lower. And our formula is basically describing it in terms of left to right, where you have your x bar equal to this and your y bar equal to this. So now what's x in this case? Well, it's, for us, essentially, if we're talking about it from left to right in terms of y, i.e. low to high here, okay, that's actually our y bar. What we call x bar, if we were doing it normally with respect to x, that actually becomes our y bar. And then in the same concept, our y bar, which is going up and down in our concept here, is left and right, or x bar. So when we're doing it along the y-axis, we actually flip these things. So in terms of y-axis, for us, basically, this thing becomes our x bar, and this thing becomes our y bar, but in terms of y. So we're going to go ahead and write that. Basically, y bar is our x bar's formula, 1 over a integral from a to b of y times f of y minus g of y dy. And our y bar becomes our x bar. X bar is equal to 1 over a times the integral from a to b of 1/2 times f of y squared minus g of y squared dy. So this one just takes us a little bit of thinking here. Essentially, we want to make sure that we are finding this. Otherwise, we'll actually find it kind of the inverse of it. So that's basically what we're doing here, is sort of an inverse of those things. We flip our x's and our y's. Okay, now one other thing to note that I haven't really talked about here is that, like, if this was, anytime we have some sort of symmetry in our shapes, okay, basically we would know that the center point would be on that symmetry. This isn't symmetric, but it's something that hasn't really come up, but it is worth noting as a side note. That could maybe make our lives a little bit better, but we have this thing here. Okay, so let's go ahead and do this thing. So we have we'll start with our y bar. Y bar is equal to our 1 over a, which is 2/9, times the integral from 0 to, or not 0, it was from -2 to 1. -2 to 1 of our y times f of y. In this case, that thing here is going to be our -y plus 2 minus g of y, y squared. Now, if you ever get the order wrong as well, something to note, you'll just get a negative. It's not the end of the world. All right, just flip that. Okay, so that's this thing, and it's dy. So we'll go ahead and integrate this thing then. Well, y bar is equal to 2/9 times the integral from -2 to 1 of -y squared plus 2y minus y cubed dy. So that means then that our y bar is equal to 2 over 9 times negative y cubed over 3 plus 2/9 2y squared over 2 minus 2/9 y to the 4th over 4. That's minus. So in this case, that was our, or excuse me, that's this thing from 1 to negative 2. All right, now let's simplify this a little bit before we move on. This is just kind of ugly. This needs to be simplified. So we have y bar is equal to negative 2y cubed over 27 plus these 2's cancel, and we have 2y squared over 9. Now this is like saying negative 2 over 9 times 1/4. This becomes 2, this becomes 1, this is 18. So we're going to have minus y to the 4th over 18. We're taking this from 1 to negative 2. Okay. So, plugging in 1 into this thing, screw it, we're going to go over here. We're going to plug it into Desmos. I'm not going to do that by hand. Negative 2 over 27 plus 2/9 minus 1/18. We're going to say minus. Now we're going to do negative 2. So that's really a negative 2 to the 3rd times a negative 2. That's really a 2 to the 4th positive over 27 plus, now that's also positive. This would be a 2 to the 3rd over 19, or excuse me, 9 minus 2 to the 4th over 18, and we get negative 1/2. That is our y bar. All right, so y bar is negative 1/2. Now we have our x bar, which is a reminder for us. Our x bar is the y bar normally, and we're going to use this 1 over a 1/2 f of y squared minus g of y squared. So let's go ahead and write that out real quick so we have it. So our f of y squared would be negative y plus 2 squared, which is going to be y squared minus 2, which is minus 4y plus 4. And then we have we're going to do a minus our g of y squared, which would be a y to the 4th. That's what we're going to be taking here. So I'm going to get rid of that. So this is what we are taking here, and we're going to take 1/2 of this thing. So I'm just going to copy it down here to make my life a little bit better. Okay, so this is our f of y squared minus g of y squared. That's what this thing is. Okay, so according to our formula then, our x bar is equal to 1 over a times the integral. So as a reminder, our 1 over a is 2/9. So we have 2/9 integral from negative 2 to 1 of 1/2, which just as a note, we'll cancel with that one, times this thing, y bar minus 4y plus 4 d. I cut that off a little fast. Plus 4 minus y to the 4th dy. Okay, so we end up with x bar is equal to 1/9 times the integral from negative 2 to 1 of y squared minus 4y plus 4 minus y to the 4th dy. And we can just integrate this thing pretty straightforward here. 1/9 times y cubed over 3 minus 1/9 times 4y squared over 2 plus 1/9 times 4y. It's terrible 4. Let's rewrite that. Okay. Minus 1/9 y to the 5th over 5. We're going to take this from 1 to negative 2. Okay, so let's do a little bit of cleanup work. So that will be y cubed over 27 minus, this becomes 1, this becomes 2, minus 2y squared over 9 plus 4y over 9 minus y to the 5th over 45, and this is from 1 to negative 2. Okay, so again, for my sanity's sake, I'm going to go ahead and type this thing in on Desmos. Definitely not going to do that by hand. But plugging in our 1 into this thing, we have 1 over 27 minus 2 over 9 plus 4 over 9 minus 1 over 45. Then we say minus, so here negative 2 to the third is negative 8 over 27 minus 8, because 2 times 2 is 4 times 2, that's 8/9, minus 8/9 that would be a negative, and a negative makes a positive. 2 to the 5th over 45, which gives us some value here of 8/5. Okay, so let's go ahead and see. This is our x bar. X bar equals 8/5. So that means our center point is 8/5, comma, and negative 1/2. All right, so let's see if that's believable. 8/5, comma, negative 1/2, and it's pretty darn close to our guess. All right, cool. So that is definitely then believable. All right, so that's our center of mass. Now, one of the things about, or our centroid, or our kind of center point, balancing point, whatever we want to call it. Now, one of the interesting aspects of this center that I want to bring up, but I'm not going to really go into too much, but I want to at least mention, is that basically we have these theorems of Pappus. So let R be a plane region that lies entirely on one side of a line L in the plane. If R is rotated about L, and then the volume of the resulting solid is the product of the area A, or I should say then the volume of the resulting solid is the product of the area A of R and the distance traveled by the centroid. So this is called the first theorem of Pappus. So basically, if we take the area then, okay, the volume would just be the area of our region times the distance traveled by our centroid. So if we're rotating it, that distance would probably be a circumference. And so basically, we take the circumference of our centroid, or the circumference that is generated from our centroid rotating around, and we just multiply by our area, and we get the volume. So this is our first theorem of Pappus. So one of the benefits of finding that center point is if we find the center, all we then have to do is find how far that center travels in that circumference and multiply it by the area, and we get the volume. Okay. We also have the second theorem of Pappus. So let C be a curve that lies entirely on one side of the line L in a plane. If C is rotated about L, then the area of the resulting surface is the product of the arc length of C and the distance traveled by the centroid of C. So again, this area here then is going to be the product of our arc length and our centroid. And this is our second theorem of Pappus. Now, in general, we don't necessarily need to use these. They're just kind of interesting aspects that if we knew the centroid, it could make finding volumes or areas potentially easier, depending on the situation. Now, obviously, arc lengths kind of suck, so we probably would avoid that one as much as we can, but who knows? Maybe the arc length would end up being something nice that normally our area wouldn't have been. So, again, these are just some additional uses for that center. And we'll talk more about these center points when we talk about probabilities as well, because that's also somewhat useful. So, that has been our applications of physics and engineering. Strictly speaking, it's the moments of centers of mass. So, thanks for watching.